Hello everyone, thanks for coming to our week 3 review of linear algebra. So in this week, we introduce matrix transposes, symmetric matrices, and then a brief introduction of the vector space chapter. So the transpose basically flips the rows and columns of a matrix. The transpose has many nice properties. For example, the transpose of the summation of two matrices equals to the summation of the two transposes. The transpose of a matrix product AB equals to B transpose times A transpose. And transpose is interchangeable with inverse. A symmetric matrix is a square matrix such that its transpose equals to itself. Symmetric matrices lead to the factorization A equals to L d L transpose, where elimination proceeds without role exchanges. Specifically, given any matrix R, RT, R, and RT are always symmetric. Such matrices arise naturally from rectangular matrices and many differential operators. Usually, tree-diagonal and band matrices that preserve spatial structure greatly simplify Gaussian eliminations. Positive definite matrices have positive pivots, which require no exchange when doing the Gaussian elimination. And if a matrix is symmetric and positive definite, it would always preserve symmetric decomposition. A equals to L transpose. They are very good for and suited for numerical computation. Then we introduce vector spaces and subspaces. A vector space consists of vectors together with rules for vector addition and multiplication. Those operations must satisfy the 8 axioms: closure, associativity, commutativity, existence of zero and negatives, and distributive laws. The standard examples are Rn, whose vectors are column vectors with unreal components. We can also consider a complex component. The definition is abstract because vectors need not be columns. They can be matrices, functions, or infinite sequences, or essentially anything. A subspace is a non-empty subset of a vector space that is closed under addition and scalar multiplication. Every subspace automatically satisfies all vector space axioms, and each subspace must contain the zero vector. The smallest subspace, however, is a set containing only the zero vector, and the largest subset is a whole space. Especially, the dimensionality of the smallest subspace is zero. Given a matrix, there are two very special subspaces. One is called the column space. The column space CA is the set of all linear combinations of columns of A, which is a subspace of our M for an M by M matrix. It consists of all attainable right-hand side B, for which AX is equals to B is solvable. The null space NA is the set of all solutions to the homogeneous equation then AX equals to N. It is a subspace of Rn. The structure and dimensions of CA and NA reflect key properties of A, including independence of columns, and solvability of linear systems. Given a matrix, we then introduce its echelon form. A matrix can be reduced by elimination to an echelon form, with each pivot is the first non-zero entry in its row. Zeros below each pivot. Pivots move to the right as we go down. So this is why it's called the echelon form. Zero rows appear at the bottom. Maybe there is no zero row, of course. We also have the reduced row echelon form after we perform further operations on the echelon form U. Each pivot equals 1, zeros above and below each pivot, and R is unique for each matrix. If A is square and invertible, then the reduced row echelon form would always generate the identity matrix. Given the echelon form, we can define the pivot and the free variables. Pivot variables correspond to the pivot columns, and free variables correspond to the non-pivot columns. When solving Ax equals to 0, we can reduce it to Rx equals to 0 and we assign arbitrary values to free variables. After that, we can solve for pivot variables. Each free variable produces one special solution. Then we can have a more clear understanding of the structure of the null space. All solutions are linear combinations of special solutions. The null space is a subspace of Rn spanned by the special solutions. The dimensionality of the null space equals the number of free variables. That is the dimensionality, that is the number of linearly independent special solutions. Thanks for listening.